And this is a joint talk with my colleague Paul Prini from University of Windsor. Our topic is on reduction of computational errors or the pursuit of correctness. Here's the outline of my talk. We're going to go over some examples and remedies, and then we'll go on to look at a case study, summation with MPI, and then summation with OpenMP. And then we'll talk about some future topics, and then we'll point it out some reference points to the audience at the end. So examples. First example, rounding errors. The number, the base 10 number, 0.01, you may or may not be aware that it is not representable exactly, but approximated in base 2 number systems on computers. So if our input data contains numbers such as 0.01, we immediately have an error. So how much is this error? How much is this error? This C code shows something interesting. So this is a very short code. We define a variable x, which has a value 0.01 stored in the single position floating point format. And then we'll print it out in a full precision representation. And this is what we got. 0.01 is actually in the machine stored as this number with a whole bunch of digits after the decimal point. And let's see what is the approximation and where does this approximation come from. So we're using a computational tool called the Julia. Julia is interactive computing environment and also a high-level language for scientific and parallel computing. Let's see what 0.01 is stored internally in single position, stored internally. For single position, we're using a 1 sign bit, an 8-bit exponent, and a 23-bit fraction as shown on the right-hand side. So 1 sign bit and the 8 bits for the exponent and the 23 bits for the fraction. Sometimes it's also called mantissa. The output spit from the Julia code is this binary representation with bunch of zeros and ones. So we first will calculate the component, and if you read it carefully, maybe you can read it afterwards with the PDF file, and we compute the exponent and minus the bias, which is a 127, and this will give us -7. And then we calculate the fraction, and we're just counting from the ones in this fraction part. So the first one is 2 to the power of 2, -2. The next one is 2 to the power of the next 6, and so on and so forth. And then we calculate this fraction part f. And then we get this normalized form, 1 plus f fraction times 2 to the power of exponent. And then this gives us the value that we see from the C code. So what is the approximation error here? The approximation error will be the difference between the actual number 0.01 and this machine represented number, which is 2.23 and the times 10 to the power of -10. Well, you may say that this error is a small. It is a small, but this number is this kind of errors is not are inevitable. But keep in mind, however, they can be accumulated, and magnified in your computation, and sometimes might cause problem. Next example, rounding errors in input and output data. And often we use the output from one program and read it in as the input for another. If we're not careful enough with the format of data stored, and we will bring in errors. So here's an example. We generate array A in single position, 10 numbers, and then we write it out to a text file. And then we read the data in from this text file and then store it in array B. So array A is generated, and we write it out in a text file, and then we read it back into array B. Now they look identical with this format. They look identical, but if we compute the errors element-wise and present them side by side together, we see, although A and B look identical, but we do see the error, and the error is not small. So how do we fix this? And the one remedy is to save the data in full position and with maximum digits defined by standards. So in this case, we store the data again. A and B are in single position. Just for the purpose of demonstration, we use the single position, just so they're easy to see the error. So instead of writing the array elements A out by default, using the default format, we're using the full position, the format for a full position with the maximum digits. This maximum digits is a constant float decimal dig. This is defined in the standard, and it is available in C and C++. Okay, we write this thing out again into the file in a text format, readable text format, and then I read this data in from the text file that we just generated into array B. And then we calculate the error again. Now we see 0 because we store the data in the exact format and then read it back in, so we don't see the error. Another way is to save the data in full position using hexadecimal format. This is supported with the %A specifier in C or hex float function in C++ and the EXEDIT descriptor in Fortran 2018 standard. Okay, and we generate the data A, and then we write A out in the hexadecimal format, and then we read the data back into array B, again in the hexadecimal format, and then we compute the error, and we present them, print them out side by side. We see 0 errors. Now, just keep in mind here that the hexadecimal format is the exact format, is the full position format we're using for storing data, floating point data. Okay, and some comments here. Saving data in a maximum number of digits is the simplest way to preserve the accuracy of data, but one must pay attention to the format for the portability between languages. Second point, the hexadecimal form keeps the exact representation of the data in the floating point format and is therefore more reliable. However, it is not generally portable between languages. It is portable between C, C++. However, for example, C Fortran code cannot read the data output in the hex float format by C or C++, and vice versa, as of now. And next point is the C++ and C and C++ use a normalized form, and while Fortran doesn't, as of the standard 2018 standard. And in addition, the EX descriptor in Fortran for a hexadecimal format isn't yet supported as of a GNU 4, the version 14. It isn't supported by the Intel compiler, for example, though. But the general advice that we would like to give to the audience is a binary form or more network portable forms are encouraged to be used for I/O. You can use the simplest way, use the maximum number of digits if your data set is not large, and that perhaps the simplest way. But in general, you're better off using a better, more portable forms. Next example, I call it the incorrect odometer. In this C code, what we do is we add number 0.01 repeatedly 100 million times and see what we get. And just by math, if we add 0.01 100 million times, what we should have is a number that 0.01 multiplied by 100 million, and then we just cross two zeros. Okay. So this is what we do. We use a for loop and to repeatedly add a 0.01 to the variable meters. And this is what we got. In the end, we just divided by 1,000 to get the kilometers. So what we expect to get is 1,000 kilometers. What we actually get, however, surprisingly, is 262.14 kilometers. This is there is a huge difference. And the cost is during the additions, and two operands are out of range. Why? Because when meters is getting bigger and bigger, compared to 0.01, they're just out of range. Meters is too big, and the 0.01 is too small. When we put the two numbers, two extreme numbers together and try to do addition, subtraction, and we lose the accuracy. And the plus here, we store the meters in single position. A single position only gave us up to 9 digits, but most the reliable digits is up to 7. Okay. So here's a simple fix. We simply just change the position from a single position float to double for double position in C or C++. And then we can see that we get the right answer. Just forget about this one because I just add one more in one more iteration. Okay, this is a simple fix. However, I would like to present yet another way. We're still using float, single position, and to try to get the answer, the correct answer in a more complex way. And this is through the grand sum compensated summation. So what we do here, in the for loop, we insert 3 lines. We define the variable y. which is 0.01 minus a C. C is what we call the compensation. And then we define another term, T. T is the meter, which is a sum plus Y. And then we define a compensation, C, which is T minus meters minus Y. Now, if you look at this carefully, there's no fancy math here, but if you look at this carefully, you will see, oh, wait a minute, this C is 0, isn't it, algebraically? Because C is T minus the meters minus Y, and T is meter minus Y. So it turns out, if you do the math, C is 0. So therefore, when we say meter is equal to T, and essentially it works out, we're having a assignment on the right-hand side, we have meters plus a 0 plus 1, which is exactly the same as the left. So there's some complex theory behind the scene here, and that's proposed by Cahan, compensated sum. We're not going to go into the details, but just show you with this magic, and without changing the position, we get the correct answer. And you might ask why you want to apply a Cahan sum as opposed to use a double position, which is simple fix as we just saw. The answer is sometimes using a single position will save a lot of space, and as well time. When the memory becomes expensive, and you might want to consider to take as less space as possible. Therefore, there's a reason for using a float, using a single position, rather than double position, which will waste both memory and the time. And with some tricks, we can still get accuracy. And this is a weighing situation. So this example shows different ways of getting the correct answer. Next, let's look at a slightly different problem. We're solving a ill-conditioned problem, but this is inherited from the problem itself. We're solving an ill-conditioned problem, AX equal to B. In this case, matrix A is a 2x2 matrix, and you can probably tell these two columns are linearly dependent because the column 2 is almost nearly the column 1 multiplied by 2. There's a slightly difference. So what we do is we generate the right-hand side B by multiplying the matrix A with a unit vector. Then we get the right-hand side B. And then we use this matrix and the right-hand side B to solve for X and see what happens. If we do math correctly, we should expect to get exact the answer, which is unit vector. Let's see. Now, we're doing this in MATLAB. And first, we change the right-hand side B that we calculated by just a tiny bit. We changes this an element, which is a 3, and then we add a 0.002, and then we get a 0.3, and this is a typo. And then we solve for X. Now we see the solution. This is a solution, which is a way off unit vector. And next, we change the elements in A so that we change the first column, and then we solve for X. And then we get a different answer, which is also away from the unit vector we expect. So by doing this exercise, we changed we made some changes to the right-hand side and the matrix A. and we got two very different answers. This is this is kind of like a real situation. You're solving some problems, and we have the right hand side and left hand side, right hand side B, and the left hand side the matrix A. And if we import the A and the B into a computer, and because of the approximation error, which means we made the changes to the matrix A and the right hand side B, we got a solution. Then by looking at this example, we might ask ourselves, how do we know the solution we have obtained is correct? Which one is correct, or which one is more correct? How reliable is the computer solution? If we have a small change in the input and we see a large change in output. In this example, we know, I mentioned ahead of time that we're solving ill condition a problem, but in the real life, we don't often know first time that our problem is ill conditioned. So it raises a question, a challenging question, the answer we obtain, can we trust it? Next example, again, is an ill condition problem. Now this time, our matrix is Hilbert matrix. It is a famous matrix, Hilbert matrix. For those of you who are familiar with the MATLAB, Hilbert matrix is predefined. And the Hilbert matrix of rank 6 is defined in such a way, which is pretty easy to recognize. And then let's see how we do the exercise and example. Again, this is Hilbert matrix of rank 6. And again, we're just we're following the same technique. We will construct our right-hand side B by multiplying the Hilbert matrix by a unit vector, and then we solve for x and see what we get. So we try different sizes. We start with size 10, and then increase the size to 11, 13, and 50, and then look at the solution. Now, just keep in mind that the right-hand side B is created by multiplying the matrix, Hilbert matrix by a unit vector, and then we solve for x. And if we do things correctly, algebraically, we should get the solution x identical to a unit vector, but in the reality, in floating point operations, we don't. Let's take a look at the solutions we got. Here for size 10, we got this, which looks like it close to a unit vector. And for size 11, it's not too bad, it's close. Size 13, we got something just as things have started getting going south. And for size 50, which then we see that's a totally wrong. Now let's examine the relative error. For size 10, we compute the relative error, which is the solution, the difference between the solution and the unit vector. The relative error is 0.00026 for size 10, and for size 12, it increases to 50%. And the 50%, we know that if the relative error is 50%, that's totally not acceptable. Now, the one thing that we should keep in, what you should know that Hilbert matrix is has a closed form for the inverse, for its inverse. So Hilbert matrix itself is not singular. Therefore, the inverse exists. So in order to get the solution, why can't we just multiply the inverse and then get the solution and see if we can get the identical answer? But the problem is, although the open matrix has a closed form for its inverse, but if you look at the numbers for size, for example, greater than 12, those numbers cannot be represented exactly in IEEE double position. So therefore, we cannot expect to get the correct to get the exact answer by using the inverse, by multiplying the inverse by the right-hand side vector b. Okay, and you can do this perhaps using a symbolic algebra system, but that's not the point. The point is whether you want to solve this equation using a solve for the linear system using LU decomposition for this equation, or you want to multiply the inverse matrix, which has a closed form, by the right-hand side B. Either way, you won't get the exact answer just because of the number, because the matrix, Hilbert matrix ill condition, and the second, the inverse matrix cannot be represented exactly in IEEE double position. Okay. So what do we do? Now we have to turn to some other tools for help. In this case, we're using a multi-position laypack routine, which is a linear algebra routine, but in multiple position. And for size 13, we're using a position around the 30 digits, we get a solution. We get a solution. The solution looks very close to the unit vector. We calculate the relative error. See, this relative error is 5.8 and times 10 to the power of negative 14. Okay, so this is what we're using a multi-position tools package for solving a problem to the position, to the accuracy that we want. Okay, next, we're going to advance to a different topic, reduction using MPI for summation. The problem we're looking at is a summation of an array. We generate an n element random numbers and stored in single position. Those values of elements are between 0 and 1, uniformly distributed random number. And this is the pseudocode. We set the sum, the initial value to the sum, and then we just repeatedly add the number, add the element to the sum, and we get answer. Now, we do this in two different ways. First, we do this sequentially. We go from 1 to n, and we get a sum. And then we're using alternating procedure. First, for all numbers, odd indices. And then we do odd even indices. And here's the answer. For a sequential format, we got this answer. This is the total sum for 1 million elements. And for using alternating loops, we got another number. And then the question is, which one is more close to the choose? Or what is the choose? What is the actual correct answer? And how significant is the difference to your work? And to see the answer, how close is to the answer to the choose, we performed the same procedure using double position. And using double precision, we get this answer, 500,144.93. And we trust this answer correct because the IEEE standard guarantees the accuracy to certain digits. Now, the question is, can we get the same accuracy again as we saw before with a single position? Using double precision, we get this answer, and we trust this answer is correct. The question is, can we get the same accuracy with a single position? The answer is yes, and this is how we do. And we apply a compensated sum variant called a Babushka-Neumayer algorithm. This is, I'm not going to explain this algorithm here. It just take it for granted. This is what we use. Again, it uses a compensated summation. This compensated term is a C, and after the calculation, we add a compensated term to our answer, and we get the answer with this algorithm. We get the answer 500,144.93, which is the same as what we get for using a double precision to certain number of digits. Okay. Now, we're going to do this using MPI in parallel. How are we going to do this in parallel? Still, we want to add n elements together and to get the total summation of array A. This is what we do in our example exercise. So we generate n random numbers, and then we distribute n elements to p ranks, and this array is divided into p chunks, and we scatter them. We put them on p ranks. By ranks, I mean the MPI process. That's the term for MPI process. And we call them rank 0, rank 1 to rank p minus 1. And our procedure is as such. On each rank, on each MPI process, we compute the local sum. And then we call the MPI reduce, which is a reduction procedure to combine the local sum together to get the global sum. This is what we do. This is the procedure. Distribute arrays to MPI ranks, P ranks, and then we calculate the local sum within each rank, and then we call the MPI reduce to get the final answer by aggregation. And this diagram shows that the concept, we have a P ranks, and after we're done with the local summation, we got the local sum S1, S2 to SP, and then we call the MPI reduce to aggregate the sums and to get the final answer. And here's what we've got. We generate an n number of elements, random numbers, and we distribute across p processes. And the result with 1 million, this is what we get. We we vary the number of processes, and we look at the summation we get. Again, we compute the summation using a single position. As we see, when we're using a different number of processes, and we get a different values. If you consider this a dollar value, and the difference is as much as $20. So next, we want to apply our compensated summation to this example and see if we can get accurate answer, as we did in this in the serial procedure. So again, we generated n random numbers and distributed the chunk of arrays to p processes. And then the procedure is, as before, we compute the local sum with the compensated sum algorithm. And then we call the MPI reduce with a customized sum operation with the compensated sum procedure and to get aggregated global sum. So now the diagram becomes this. After the local summation, we got the local sum S1, S2 to SP plus a compensate term C1, C2, and the CP. And we want to combine them and aggregate to get the final answer and see what we get. The MPI call we use is MPI reduce. Well, here, there's some technical details, but don't worry, if you're not familiar with MPI, you can just totally ignore this and wait for the next slide to see the answer. For those of you who are familiar with the MPI, and just please take a look at what's new here I'm using. So this is an MPI reduce call. It takes the input, which is a local value, and then it returns a output, which is the aggregated the result. In our case, the first will be local sum, and the next will be the global result, global sum. And the count, in our case, that will be just one element. And the data type is a float. We're using a single position. And operation is aggregation operation. That's a sum, MPI sum. And the root rank, they always put the root rank, which is 0 here, in the communicator. Okay, there's nothing new here in the MPI reduce call. What's new is instead of using MPI sum, we're using customized MPI, customized summation. Sometimes we call this a callback function. So I define my own function to deal with the summation. I call it my sum. This is my function. My function, by MPI standard expects that if you define this as your own function, you need to take these two elements. First, the input, and the second is the input and output. Both are array, and you define the size of array, and you define the data type. This is a very generic form for customized function to be defined for using MPI reduce with customized operation. So what we do, the extra work we need to do is we need to define a data type required by this MPI standard. And we need to define an operator, which is our my customized defined function, my sum. And by calling this MPI op create, and it takes my function and it returns the pointer to operator. And then I use this operator to feed into MPI reduce, and I feed in the local sum and the global sum. Now, this time the global sum takes two values. One is the aggregated the value to be returned, and the second is the compensated term. It provides a way for me to add that compensated term and then get a result. Now, compare this highlighted in yellow with the regular MPI call. The regular MPI call, for those of you who are familiar with, you will just take the local value, you get a global value, and count the number of elements. In our case, because we're just adding numbers together, that would be just one number. The final number is one, and the data type and the MPI defined operation, which is a sum, as opposed to here, we're feeding different parameters. Now, without going into much detail to the MPI calls, this is what we got with Kahan, Babushka, Neumayer compensated algorithm with MPI for 1 million elements using different number of processes, and we got pretty much the same answer, and they're more consistent, and we succeeded in this case. Next, we're going to look at how we're going to do this with multi-threaded code using OpenMP. Now, I just simply put up the OpenMP code here. This might require a little bit of knowledge with the OpenMP. Suppose I have a C code here. This is a C code within this OpenMP parallel region. What the C code does is simply does the local sum with the Kahan, Babushka, Neumayer algorithm, and then we put a OpenMP pragma here. It says to compute this, do not wait. To compute this independent of each other, and in the end, after every thread is done, we add the local sum together. So this is a synchronization point. Okay. And then let's take a look at the result. We're using a different number of threads, 1 to 12, why 12? Because I did this experiment on my laptop. My laptop has 12 cores, and I just ran as many as 12 cores. And again, we see pretty consistent result, but we see there's a little difference. But at this point, I cannot explain why I have a slightly different answer. It might have to do with the order of the threads operation or something else that I have to look into in details. Okay, so this completes my talk, and I just put up some future topics. We're going to have some more explorations of floating point number operations examples. And we might want to look at some compensated summation in reduced operations in multi-threaded cases. We've seen examples in MPI and multi-threaded code using OpenMP. And my colleague, Paul Prini, is going to look into more complicated examples. And also, we might want to look at the compensated submissions in reduced operations on GPUs as well. And then lastly, I just put up some reference pointers to the references. First, the MP laypack routine. A package is that's a multi-precision laypack linear algebra package for solving linear problems, and created by Japanese scientist Nakata Maho. And there's another package, the MP font. This is a Fortran version created by David Bailey. And Julia language, some other works by other people on implementation for Kahn summations for MPI, and there's some other references. Okay, so I'd like to just end it here and leave some time for questions from the audience.